Hello everyone, I'm Xuan from the NeuroSpinCompute Laboratory at the University of Texas at Dallas, and today I will give a brief overview of control circuit overhead for stateful memristor logic. Memristor, or resistive memory, is a popular non-volatile two-terminal device that's been widely used as memory, neural network circuits, and some other computing systems. Here we show one of the most fundamental stateful memristor logic gate, the imply gate, which consists of two memristors and a ground resistor. For example, if we assume the memristor threshold is 4 volts and apply the driving voltages correspondingly, here we have a -3 and -5 volts applied. Then, when both memristors are in high resistance state, as logic 0, the voltage across the memristor B on the right is roughly 5 volts. That voltage across the memristor B exceeds the 4 volt threshold and send memristor B into a low resistance state as logic 1. Similarly, all input combinations are shown here, and where we can simply use the two memristor to implement the two input Boolean logic function, which in this case is implication logic. Memristors have therefore been claimed to provide logic efficiency improvements, especially with smaller area and lower device count, as shown in the table to the left. However, this comparison is unfair, since memristor logic circuits require multiple driving voltage to be applied sequentially, and the CMOS overhead circuitry to provide those control signals is not free. So what happens to this comparison if we include the overhead control circuits? Here we show a CMOS controller circuit for stateful memristor logic, where a diagram on the top shows the structure of the proposed controller. On the bottom are the simulation waveforms of a memristor NAND gate on the left and the memristor 1-bit full adder on the right. The table on the left summarizes the device comparisons between pure CMOS and memristor logic with CMOS overhead, and the right table shows the energy delay products comparisons. The result shows that memristor logic needs a large number of extra transistors and has more than 10 orders of magnitudes greater EDP. Well, it is possible to optimize this controller circuit by a bit. There's no way to compensate this huge difference. Here are the conclusions, and I think the main takeaway of this poster is that the stateful memristor logic is not a viable alternative to CMOS for conventional logic applications, but it is potentially useful in other architectures that exploits all advantages of these memristors. Here are all contributors of this work. Thank you, and I'll see you in the conference.